Hello, welcome to this class of titrations where we are talking about the photometric titrations, because we are using a photometer to identify the endpoint of some titrations. So, now we will introduce something where we can see that a particular reagent which can be a complexing agent. So, what is that? That means like that of our chromophoric agent, what we are talking about so far in our some previous classes, where we have seen that the chromophoric agent which can react with some analyte with that reagent, giving you some product, and product have some specific color which can absorb at a particular specific wavelength of lambda max. Now, when we talk about the complexing agent, definitely it is a corresponding complexation reaction we are trying to study. So, A will be your analyte, which several times I already told you that it can be the corresponding metal ion, and this can be your ligand. As we all know, the metal ion when react with the ligand anion or the neutral ligand give you the corresponding complex. So, we call this ligand as a complexing agent, and that complexing agent, as we discussed earlier also, that one such very good complexing agent is EDTA, ethylene diamine tetraacetic acid, and in the tetraanionic form. So, this EDTA can be used nicely to detect the endpoint where the EDTA can bind to the metal ion, and where we have seen that we can use some metal ion indicators also, like areochrome black tea, areochrome black tea was used for a direct or manual titration. So, this we all know, like our manual titration for acid base reactions. So, here all these cases when we introduce some photometer or a spectrophotometer, our basic intention or basic idea is that we have to have some colored product or the colored metal ion or the colored ligand, such that we can monitor the corresponding absorbance during the titration process. So, if we ask ourselves some very basic question, that how will you get a photometrically detectable endpoint? That means, we are looking for something where the corresponding change in absorbances will show or detect the endpoint of any analysis. It can be your analyte, it can be your metal ion, or it can be anything else where there is a sudden change. That means, it can show the endpoint very nicely, where you have two linear part, one is going before the endpoint and another is going of different slope after the endpoint. So, in case of simple acid base titration, if the reaction, that means the reaction of analyte and reagent, we are consuming the analyte which is suppose your base by the acid, we use some indicator. That means, for simple acid base reaction, what we do, they do not absorb in the corresponding wavelength range. So, we introduce indicators. So, indicators of two forms, say HIN as we know and IN minus, and there will be a sudden color change. We can monitor that also by doing the corresponding photometric titration. So, we can detect the endpoint which can be your photometric endpoint. So, for this titration also, if we now know that this thing, that means your reagent is same and we are looking for the analysis of say 2 metal ions, which is M1 and M2. These two can be of different charges also. So, if both of them can bind to this EDTA and that binding constant or the formation constant, if they are different, so the species, that means the metal ion which is having the higher value magnitude of the corresponding stability constant or the formation constant, what we call or what we indicate in terms of the K value. So, if the K value for this particular metal ion say M1 N plus is more, so this metal ion can bind EDTA nicely and we get, if this is a colored one, we get a change of the corresponding absorbances. But if it is not, what happens that when all the M1 is exhausted, during that time the M2 will not bind to your EDTA. So, when all the M1 will be exhausting, so at the end point of that particular case, your absorbance will change or will increase going from this titration where the M2 is being consumed by your tetraanionic EDTA. So, this is one such example we can see now by saying in the form that if we have two species and two are completely different, one is bismuth 3 plus, another is copper 2 plus, and we use EDTA 4 minus for its neutralization reaction or the complexation reaction. So, we choose a wavelength 745 nanometer, where both the cations, that means these two, as well as the reagent and the corresponding bismuth complex. So, remember these three things, that this cation and this cation is silent or is not absorbing at this particular wavelength of 745 nanometer, as well as the bismuth EDTA complex. So, what we are looking for? We are looking for the corresponding complexation of copper 2 plus and EDTA. We all know very nicely that 1:1 complexation reaction goes very well. So, we will detect that particular one. So, when this bismuth is getting exhausted like your metal ion M1, we get something, some slope of the corresponding absorbance plot. Then when all the bismuth has been consumed, we get the corresponding complexation reaction between copper 2 plus and EDTA. So, if we try to have the corresponding plot, what we see that we will be adding milliliter of your EDTA solution, which is 0.1 molar EDTA solution. It is a disodium salt, most of the time we use, and it is the absorbance axis. This starting from here, it is 0.03, 0.09 and say 0.15, only up to 0.15. So, what happens that this particular case, you have a straight line part in this particular point up to this particular point, then there is a increase in the absorbance which is cutting over here, and then after this point we have again a almost horizontal line. So, this basically gives us something, and after this incremental addition of this volume of EDTA, these are the corresponding points. So, we get these points also for the titration. So, when we plot these, we get this. So, how can we explain this particular plot? that means in this particular range, when this 0.1 molar DDTA has been added up to this much volume. So, what we get is that in this particular case your bismuth is complexing with your EDTA with a formation constant value of say 6.3 into 10 to the power 22, which will be higher than the corresponding Kf value for copper EDTA. So, at this value we do not have any change in absorbances. So, no absorbance change or no absorbance till all this bismuth 3 plus is consumed or titrated. So, this is therefore shows you that the corresponding end point of your bismuth. Then your copper started consuming. So, this particular point is our bismuth 3 plus end point. So, after that what we get the corresponding complexation reaction between copper and EDTA, which has a corresponding Ka value of 6.3 into 10 to the power 18. It was 10 to the power 22 and it is 10 to the power 18. So, when all of them has been consumed, that means the EDTA has been consumed by this particular bismuth. So, then EDTA will try to react with your copper 2 plus. So, this will go on increasing till we reach this particular point, which is nothing but your copper 2 plus like that of your bismuth 3 plus, copper 3 plus end point. And after that, if we add more and more of this reagent, that means the tetrasodium salt or the disodium salt of EDTA, when we add, further addition of this particular reagent will not cause any absorbance change. So, no absorbance change beyond this point. So, as a result what we get this end point, that means this much volume of EDTA is equivalent to that of your bismuth present in the solution, and from here to here, that means this volume to this volume, if we subtract this volume, this will also give you the corresponding end point for the copper for this complexation reaction. And beyond that, we have consumed all the bismuth as well as all the copper. So, is basically not, there is no change of this corresponding absorbance, because the copper has also been exhausted. So, this way we get the information that a typical reagent such as EDTA 4 minus or other complexing agent or other complexing agent can be used for this photometric titration reactions, and in one of the case, that means the metal ion with the EDTA complexation should absorb. So, we can handle aluminum with any transition metal ion, because most of the time we see that the transition metal ions are giving some colored species for absorption in these photometric titrations. So, this can give rise to some important information, that if we can have some complex ions in solution which we can study nicely by this sort of complexation reaction. So, what we can find? We can find the composition of that complex ion and also the corresponding Ka values, because just now we have seen that the difference in the corresponding Ka values for bismuth and copper with regard to your EDTA can be found out. So, when the Ka value is high, it will go for corresponding complexation smoothly with EDTA first, then the second species will go and bind. So, composition means what you can have, whether you are getting for a 1:1 complex, 1:2 complex or 1:3 type of complex. Such as one example of that ligand, we all know that 110 phenanthrone, which can bind very nicely with ferrous ion. So, we get this particular complexation reaction and we can study this for its composition, and we find the corresponding stoichiometry or the composition of the complex. That means, this iron 2 can bind with your ligand L as ML3, and this K value can also found out for this is in the range above 10 to the power 20. So, it is 2 into 10 to the power 21. So, we can follow 3 different techniques basically, where we can monitor these absorbances and the composition, how it is changing. That means, when we go for the thing what we have just seen, the titrations with M plus L forming some species MLN. So, what is the value of this N? This is your value 1:3. So, this is giving rise to some complex, and when only one of such ligand, if these are all different. So, N value if it is 6, as we have seen in case of iron thiocyanate, we see that when one of the thiocyanate is bound to the ferric ion, your color is changing. So, we can monitor that coloration for a stoichiometry of 1:1 only, but in some other case, until and unless you reach the corresponding stoichiometry of 1:6 is a hexa coordinated one, L is a monodentate one, we can find out the corresponding stoichiometric composition of the metal ion. So, first particular technique is method of continuous variation. As the name implies, that we will vary the corresponding concentration, and if we just try to measure the absorbances, and in this case what we plot is corrected absorbances with that of the corresponding volume of M and the volume of L. That means, the volume fraction we can plot. So, it is the volume of the metal ion divided by the total volume of the metal ion plus the ligand. So, that change how the corresponding volume of this metal ion can go for the corresponding change in the absorbances. So, this will go like this, and then this just basically will decrease. So, this decrease is due to the corresponding dilution of the corresponding formed metal ion complex, because with the addition of more and more of the volume of the species such as is your metal ion, it will decrease in that particular point. So, if we just extend the corresponding straight line part, so we just there is a cross section over here. So, what you find that the deviation, that how much it is deviated from that particular part. So, that will also indicate about the corresponding stability of the metal ions complex species. So, when this particular one is 1:3, your Vm by Vm plus Vl value will be 0.33. So, at this point when we plot this as the volume fraction, we can find out of that then what is the magnitude of this volume fraction, where we get this changeover or the intersection between these two straight line parts. We can find out from there that your stoichiometry for the complexation is 1:3. And in a similar fashion, the second technique what we can use is your mole ratio method. In that particular mole ratio method, what we see that we have this M and L. So, the corresponding ratio of the ligand to that of the metal ion if we plot these versus absorbances. So, this is the corresponding mole ratio, that means either the ligand versus metal ion or the metal ion versus ligand we can plot, and that mole ratio method can also be useful to determine the corresponding composition and the corresponding formation constant for these species. So, these absorbances again we can plot with that moles of L by moles of M, and when we get these, in one particular case we get the plot like this, and in another case it is something like this. So, these are the two cases of specific example where we see that if we just extend these two parts. So, this is the thing. So, this is one such magnitude, and if we go for the second one, this is also one thing. So, this is for the first one is for 1:1 complex, that means this is equivalent, the mole ratio is equivalent. When 1:1 of this is mixed, you have the maximum absorbances for this particular case, and when it is less than that, so we have to have the corresponding complexation reaction is 1:2 complex, we get a different plot. So, in all these cases what we see that the corresponding complexation reaction which way it is giving you. So, in some case this particular one, that means the method of continuous variation is useful. Just now what we have seen, and we can determine that for a 1:3 type of complexation, 1:3 the mole ratio is 1:3, but in two other cases where the complexation is 1:1 like that of our EDTA, because this is we have seen just now that for your copper or bismuth. So, copper 2 plus is to EDTA 4 minus will be 1:1. So, that 1:1 ratio is useful there and can be found out through this particular technique. And the last one, the third one is basically the one where we can see a slope ratio method. Is a slope ratio method where we can handle them as for weak complexation reaction, weak complexation reactions, where we see that in all these cases, unlike the other cases where we see that the complexation is very strong and we have a very high magnitude of K values, but this particular case the weak complexation reaction where the K values are small, and we go for this, and obviously it has some important things to remember there, that is being forced, that means when we add ligand is forced to complexation reaction, and that we want to monitor. And this particular case also that we should have the corresponding follow up of the Beer's law. The Beer's law is followed, otherwise we cannot use this particular process, and only the complex like that of our copper EDTA complex, only the complex species absorbs at the wavelength chosen for the experiment. So, these are the things that how we can monitor and how we can use all these complexation reactions starting from the different methods. We can utilize that, and the photometric titrations or the photometry identification as well as the determination of the corresponding Kf values are also useful in all these cases. So, in the next case where we can move basically another important technique of spectroscopy, which is unlike your UV visible spectroscopy, will be utilizing the radiation in the infrared range, which has a very tremendous scope, where the infrared radiation which are weaker in nature, and that infrared radiation will be utilizing for identification of some of the molecules and some of the other species very nicely. So, what we get over there, that infrared absorption. So, when we use this like that of our UV visible radiation, that IR radiation should be there and some species should be available like that of our molecules, atoms or ions, whatever species is present over there can go for absorption. So, that absorption, so the magnitude of absorption and the characteristic magnitude where it is absorbing is also interesting to know to identify the nature of the corresponding species. So, what we see that is definitely a very useful or a powerful tool to identify the pure organic and inorganic compound, because with the exception of few homonuclear molecules such as your O2, N2 and Cl2, where we do not have any permanent dipole moment, we will not be able to detect these gases like oxygen, like nitrogen and chlorine, but all other molecular species will absorb infrared radiation. So, why do they absorb infrared radiation? Because each of these compounds or the molecules or the gases has a unique infrared absorption spectrum. Because in all these cases whatever we see, if we consider that one is X, another is Y. So, X is attached to Y and that attachment is for a particular type of bond. It can be say simple CO bond, C double bond O also, and is heterodinuclear species also if one is X, another is Y. So, this particular radiation, so this particular molecular species can show the corresponding absorption of this radiation due to this particular bond stretching. So, they are attached to this bond. So, bond stretching and bending and twisting, all the different modes of vibrations, we call them as the molecular vibrations. So, how it looks like that X is attached to Y, and if that is attached to say some spring type of thing, and if we try to elongate this bond, we know that it is some because this is the corresponding equilibrium internuclear distance, and if we try to stretch them, we get some frequency for that, and that particular one by Hooke's law we can find out something which we call as nu bar or the wave number unit. So, this it has a particular type of wave number unit which we can correlate with that of the IR radiation, and it is the corresponding match radiation which can be absorbed by this particular molecular species XY, such that there will be a typical IR absorption, and what we want to monitor is that the corresponding absorption of that particular radiation. So, any of these molecular compound can show the corresponding absorption, and if there is any corresponding match. So, the exact match between the spectrum of a compound of known structure and the spectrum of an analyte, which can be identified as the corresponding analyte. So, we know the corresponding known structure and its IR spectrum, and if that is present in that particular unknown species, we can detect that particular presence of this molecular species. Suppose acetone is there in any other liquid or any other solvent, we can run the corresponding IR spectrum, and when we record the corresponding IR spectrum, we find that the characteristic spectrum for the acetone is present, and we can find out by looking at the corresponding stretching frequency for CO, because we all know that acetone is nothing but your CH3 CO CH3, and this particular part, that means the CO part, is present in the acetone. So, this acetone solvent can give you the corresponding characteristic stretching frequency in terms of the corresponding absorbance values of these, and we call it a corresponding stretching frequency for the carbonyl function, because we all know that the carbonyl is a very unique one for all the different molecular species like that of your different organic molecules, where this particular stretching is present. So, we also see that when we get the spectrum, so when the IR absorption is taking place, so the corresponding spectrum, what we will see that this particular spectrum has a corresponding energy in the infrared region, and which can excite the different vibrational and rotational transitions. So, that we will see that what are those vibrational and rotational transitions, because so far we have seen the two electronic energy levels, the E1 and E2, and we are talking about for the electronic absorption, the UV visible absorption, which is high in the high energy region. So, these two levels are involved over there. Now, we will be talking about something where within the one particular electronic level, we can have several other vibrational levels. So, we can have the different vibrational levels and the change in energy, because it is in the low energy region. So, that vibrational energy change we will see, and that particular energy change will be responsible for its absorption. So, within one electronic level, we have the corresponding V0 is not new, is V0, V1, V2 and V3. So, these are the corresponding vibrational energy levels, and we can have the absorption from V0 to V1 and V0 to V2 and V0 to V3, and all these of the different energy values can be absorbed by a typical molecular species. So, if we look at these particular things, that means the acetone molecule, what we have seen that we can have C bond and this C bond and the C double bond, and this can also attach to these hydrogens. So, you see for this most simple one, that means the acetone molecule itself, we have so many bonds which are connected by XY combination. So, these are the different XY combination, and they will have the corresponding absorption and all these different levels. So, in this spectroscopy, what we will see that which one will be characteristic and which we can detect very nicely to determine the corresponding identity of this particular solvent molecule having this particular functional group. Okay, thank you very much.